Hello. Okay, let's do problem 21 and 22 and hopefully also 23. See if we can do three of them in a single video. So let's start with 21. It looks fun, but let's see what exactly it is about. In this diagram, each letter from A to H is equal to a different integer from 1 to 8. Okay, so basically you just put 1, 2, 3, 4, 5, 6, 7, 8 into the 8 boxes, and you want to make sure all 5 requirements are satisfied. So let's see. H is a perfect square and is 1 more than D. 5 and 8 are in the same row. C is a multiple of both G and D. It's not that C is the multiple. No, it's not a multiplication. It's just saying that C is a multiple of them. It's not a product. And B is the largest prime number in the set, and B plus G is even. So they have the same parity. And what is the value of F? Okay, so let's just finish this off. Let's see. Let me draw the thing first. So we have this, and I guess it's this way, right? A, B, C, D, E, F, G, H. And let's try to translate these requirements as much as possible. First, H is a perfect square and is 1 more than D. So it is within 1 to 8. It's a perfect square. It can be 1, it can be 4. Not 9. It's just 1 or 4, and it's 1 more than D. And D cannot be 0. That is to say, D is 3 and H is 4. These two numbers are already determined. So H is 4, D is a 3. 3, H is, okay, H is 4. Okay, so this requirement is already used. We don't have to look at this anymore. And 5 and 8 are in the same row. 5 and 8 are in the same row. We have no idea which two letters they are, but we know 5 and 8 are in the same row, like this, or maybe the other way, reverse. Okay, but it must be one of them, and this must be at one of the 3 places here, because we have got 3 rows left. C is a multiple of both G and D. So C is a multiple of G and C is a multiple of D. And C is a multiple of D, meaning C is a multiple of 3. If C is a multiple of 3, C can only be 6 because there's no repetition. You don't have another 3, so it's just a 6. So you know C is a 6 and C is a multiple of G. So G can be 1 or 2, right? G can be 1 or 2. So G is 1 or 2. And this, the translation for this is done. Then B is the largest prime number in the set. If B is the largest prime number in the set, needless to say, this is a 7. And the value of B plus G is even. So as I said, they have the same parity. B plus G is even. So B and G have the same parity, meaning G is a 1, it's not a 2. And then the question, what is F? Actually, you know, F cannot be 5 or 8 because 5 and 8 are in the same row. So it must be the top row. I don't know the order, but I don't even care because I just want to tell what F is. And it turns out that F is 2, the only number that is left over. So that's the problem. It's just a series of deduction, and it's solved quite easily. Okay, so the next, you just need to translate these sentences as much as possible, and then it is quite natural to end up with that number. What's the next? Okay, 22. Let's see. A, B, C, D has vertices A, B, C, D, involving 3 unknowns R, S, T. And AB is parallel to CD, BC is parallel to AD. Does this actually mean this is a parallelogram? I don't know, because there's no configuration, there's no diagram. So let's just play safe. Seems that there is a parallelogram, but later let's try to plot the graph and see if that is really the, let's say, the only case. Okay, and what is the value of R plus S plus T? Okay, so R is negative, B is just below the x-axis. Okay, so why don't we get started? A, B, C, D has vertices. A is negative 3, negative 2. Okay, so this is the Cartesian plane, and A is negative 3, negative 2. A is negative 3, negative 2. And what else? B is 0R, and B is 0R. We have no idea. Let's do this first. C is 610. C is a 610. Let's say it is here. Not very much to scale, but you get the idea. C is a 6 and 10. And D is totally unknown. B is 0R. So B is somewhere, you know, maybe here. And it says AB and CD are parallel. BC and AD are parallel. Okay. If, let's say, AB and CD are parallel, let me write it down. AB and CD are parallel. BC and AD are parallel to each other. So if B must be somewhere here, and if AB and CD are parallel, let's say B is here, maybe the parallel line looks like this. You know, it goes through C. But the thing is that which side is B, right? B can be oh no, I'm not talking about B. I'm talking about C. I mean, B is here, and B is here, and where's D? D can be here or here, because it doesn't matter if you just consider this a requirement. A, B, and C, D are parallel. B must be somewhere here, and D can be here or here. But again, we have this. BC and AD are parallel. If D is here, what is AD? AD goes this way. It must meet, BC somehow, right? And somehow in the middle, meaning AD and BC intersect, which doesn't fit this one. That is to say, D cannot be on this side. D has to be on the, let's say, the left side of of C. So D must be somewhere here, and B is somewhere here, and this is A, B, C, D. This is the only possible configuration. If this is here, AD goes this way. If AD goes this way, then B is below AD and C is above AD, meaning AD and BC must cross. So this is not possible. D must come up here. And then we have something like, let's say this is a D, we've got AD, and we've got BC. Okay, but I want to say this is not actually a very strict proof, but it gives you quite safe intuition. So you know this is something you can rely on. We are not doing a very strict proof here, just to let you know that this is actually not enough. If you really want to give a proof showing that this is the only possible configuration, maybe you need to do some more calculation work. But here, I think we are quite sure that this is the only possible configuration. And so here is a B and a CD. And what is B? B is 0R and D is unknown. Okay, B is 0R and D is unknown, S and T. And the thing is that, this is a parallelogram because opposite sides are parallel to each other. And we want to find the value of S plus T plus R. So what do we do in this case? Actually, this is maybe the fastest way. A parallelogram has a center. The center is the intersection of the two diagonals. And from AC's perspective, this point is 6 minus 3 over 2 and 10 minus 2 over 2. This is the midpoint of AC because AC is known. And from another perspective, which is BD's perspective, the midpoint of BD would be half of S plus 0 and half of T plus R. This is another way to express the coordinates, the address of this exactly same point. So we can get two equations from here. The first equation basically tells you that S is 6 minus 3. The second equation gives you that T plus R is 10 plus 2. Sorry, 10 minus 2. And then we just need to put them together. it gives that s plus t plus r is some mental calculation, 3 plus 8, which is 11, which is the answer to this problem. And let's see, 11 is one of the choices, so it should be B. This is the only possible value of r plus s plus t without doing much calculation. But first you need to go to the do some, it's not geometry, but do some configuration work and show at least assure yourself that this is the parallelogram, and then you use the center of the parallelogram, the common midpoint thing, to create these equations. That's probably the fastest way of doing this problem. Okay, that is problem 22. Why don't we do one more? So it should be problem 24. 23 will be done in a separate video. And 24 actually, at the end of the day, 24 is quite similar to 23. Of course, it's way simpler, but 23 is actually not an easy problem. So 24 is way easier than that. So let's look at the problem. In this diagram, circles are connected if they are joined by a line segment. So it's a visualization thing. And each circle is filled with one integer, so that the positive difference between each pair of integers is connected. In connected circles is D. So that is to say the difference between any two neighboring circles should be, two neighboring numbers should be D, okay? Always big minus small. And the sum of the 5 integers here is 54. And for how many different values of D between 1 to 20 inclusive can the circles be filled in such a way described? And let's see, first of all, how to look at this diagram. It looks like square, and there's a diagonal, but this is probably not the best way to really look at it, because it's just like we have got a starting point and we got ending point. It's connected by 3 edges, and in the middle of each edge we've got a circle. I think that's the best way of understanding this structure. So let's redraw the structure to reflect our understanding. This is the top and this is the bottom, and here we've got 3 paths. In middle of each path we've got a circle. That's the idea. They are the same. And let's say the starting number is x, okay? And this one or any one of them can be either x plus d or x minus d. And the thing is that if any two of the 3 are different, so we've got x plus d, and somewhere else we've got x minus d, and this gives us only one possibility here. This must be x, because if this is not x, what can it be? From this guy's perspective, I have to keep going up. So this is x plus 2d, you're not going back down to x. So x plus 2d, but from this guy's perspective, for the same reason, this should be x minus 2d. And since d is positive, because d is not 0, it's between 1 and 20 inclusive, meaning this is not actually doable, this is not real. So if any two of them are different, this is just the x. So this is the one let's say type 1 structure. We've got 2 structures. Structure type 1, starting point and ending point are the same, and in the middle you don't care. Maybe you just go up and turn down, or you must go down and then go back up. So any one of them can be x plus or minus d. You can choose any. Okay, this is structure number 1. Okay, a family of different ways of filling the circles. And we also have a structure number 2, that is 3 paths again. If all 3 of them are the same, okay, for example, they are all x minus d, let's say x minus d and x minus d, and what will happen? And this one could be further down, because you don't consider this as x. This is already included here. So let's say this one goes further down, so it's x minus 2d. Okay, this is another possibility. Of course, this can be plus, so it's again plus minus, plus minus, plus minus, but the three of them should be the same. And then this one should also be the same in terms of going up or down. So if everyone goes up by one step here, the next one should be 2 steps above x or 2 steps below x, given that the three of them are all 1 below x. That's structure number 2. So we have 2 basic structures. This is like you going back to your original level. This is like you keep going up or keep going down. However, I would like to say this is actually not possible. But I mean, if this is the case, what is the sum of them? The sum would be 5x plus or minus 5d, right? We've got 5x's and 1, 2, 3 and plus 2, that's 5d's. Since the signs are all the same, so it's 5x plus 5d or 5x minus 5d, meaning this sum is a multiple of 5. However, if you want the sum to be 54, there's a contradiction. 54 is not a multiple of 5, meaning this case can totally be discarded. It's just not doable given the current restrictions. And now we can safely move onto the top case, where these two are fixed and you have total freedom over the three of them. You can choose. And but actually order doesn't matter here, because we just want to find all possible d's, possible values of d. So what is the sum? The sum, of course, different possibilities, right? It could be, if it's, you know, d plus plus plus, it is just a 5x plus 3d. Or maybe it's plus plus minus, then 5x plus d. What if plus minus minus, then 5x minus d? Or minus minus minus, it's just a 5x minus 3d. That's all 4 possibilities, and this, any one of them is expected to be 54. And is this doable? And so far we don't see any contradiction, but let's figure the exact values of d type by type. It's a subtype, let's say subtype by subtype. Okay, if now this is where Chinese remainder theorem comes in. It's not, but it kind of, yeah, because you're doing a Diophantine equation, and it might be okay for you to get the first solution, but where to find the very next solution, right? And you realize that 5 and 3 are co-prime, they're relatively prime to each other. So if we get a d, the next d would be 5 away from where you are. That's the idea. This is kind of a similar idea which we're going to use in problem 24. But problem 24, as I said, is way harder. This one is okay. It's just a very simple Diophantine equation. But this time, I think we're really doing some number theories in this paper as a whole, which is actually a good thing from my perspective. But anyways, let's just look at the first subtype. It gives that 5x plus 3d is 54. So that is to say 54 minus 3d should be 5 times something. It should be a multiple 5. Probably d can be 1, 2, 3. Not a good idea, but 3 is okay, because 54 minus 9 is something 5. It's actually 45. So d can be 3. And once you get the first solution, you can just go skip by 5. So 8, 13, and 18. This gives you 4 values of d. And then 5x plus d is 54. In this case, 54 minus d should be a multiple 5. So d can be 4 easily. If you get 4, you just go 5 up. Keep going. You get another 4 of them. And second lastly, minus d is 54. So 54 plus something is a multiple of 5, meaning d can start with 1 and skip by 5. You do 6, 11, and 16. And finally, 5x minus 3d is 54. So D is a 2 in this case. D is 2, and then it's 2, 7, 12, 12 and 17. That's it. So actually, the thing is that as long as D is not a multiple 5, it works. Because you have 4 cases, but there's no one-off proof to this, I think. It's very quite specific thing because you have 4 Diophantine equations to solve. And fortunately, any D, as long as it's not a multiple 5, would work for exactly one of the equations here. And in total, it's 4 times 4, 16 of them. So 16, the answer should be E. There are 16 values of D that works. Okay, that's it. So we've done 3 videos in the 20-minute video, and we're leaving problem 23, this one, to the next video, and 25, which is a great question, to the very last video. I'll see you later.